Welcome, my dear student. So this is the second lecture of that series where we discuss about the how to take the element, where to take the element, and how to apply the constant integration. So in the first video, I have already discussed about the 6 different types of element and how to take all those elements. Okay, now in this particular video, I am going to show some of the application of this element. Okay, let us start with the session. So I have already told you that these are the different topics under which I can apply the concept. So I am trying to deal with each and every topic under this video. So you'll get the feeling that how you can apply this concept. So this is the first problem where there is a rod whose center of mass has to be calculated. Rod of non-uniform rod of length L whose mass per unit length varies lambda as kx square value. So lambda is given. So where x is the distance measured from one end and you are asked to calculate the center of mass. So for that I have to take about this kind of element. This is the rod element. Okay, so by moving a distance of x I am taking an element of dx. Now what is this dm number? So for this situation dm element should be equals to lambda times dx. Okay, now lambda here is not constant. So lambda is given as kx square by L into dx. Okay, so this is our dm number. So once I get the dm, so now I can write the formula for the center of mass. So what is the x center of mass? X center of mass is equal to integration of x dm divided by integration of dm. Okay, so x dm means x k by L. In the numerator it becomes x cube dx. Integration divided by integration of dm means k by L into integration of x square dx. Okay, so here the x is varying from 0 to L. So I have to put the limit from 0 to L here, 0 to L over there. Ultimately k by L cancels out. So in the numerator I am getting x to the power 4 by 4. That means x to the power 4 by 4 putting the limit from 0 to L. And the denominator I am getting x to the power 3 by 3 putting the limit from 0 to L. So once I simplify, so what I am getting that is equal to 3L by 4. So this is the position of the center of mass 3L by 4 from this end point. Okay, so from here the center of mass will be located somewhere over here. This is the position where this distance is equals to 3L by 4. Got it? So this is how we can apply this situation. Now moving on to the next application. Again it is a problem from the center of mass. Again you are asked to calculate the position of the center of mass of the uniform plate having semicircular inner and outer boundaries at A and B. So A is the inner radius, B is the outer radius, and you have to find the position of the center of mass. So it is a similar, it is a uniform type of geometry. So for this uniform geometry, I define the parameter sigma. Now what is sigma? Sigma is mass per unit area. So if the mass of the plate is m, so m divided by area. So what is area? That should be equals to pi r square by 2. Circle, half circle area. Okay, so it should be equal to pi into b square minus a square by 2, so it is 2m. Okay, so this is nothing but our sigma number. So once I got the idea of the sigma, now I have to take about the element. So for this element I will take the circular arc type element. So once I move a distance of r from this center O by moving a distance of r and further by dr length, I am taking this element. Now what is this area of this element? dA should be equals to pi r into dr. That is our dA number. So once I calculate the dA number, next task is to calculate the dm number. So dm should be how much? Sigma into dA. Okay, so sigma is 2m divided by pi into b square minus a square, that is the sigma number, multiplied by pi into r dr. So pi cancels out, so 2m divided by b square minus a square into r dr. That is our dm number for this element. Okay, so for this element I know that the center of mass for this ring element should be at a distance of 2r by pi. For this element, so I have to calculate the y center of mass. So y center of mass equals to how much? Y into dm divided by integration of dm. Okay, now what is integration of dm? That is nothing but our m number. Okay, And what is y? Y is the position of the center mass of the element. So for this element, the center mass is located over here. Now what is the formula for the center mass for the ring? So that should be equals to 2r by pi distance from the O. So from this point, this is our 2r by pi here. So that is basically our y parameter. So here I am writing 2r by pi into dm. So dm means 2 capital M divided by d square minus a square into r dr, whole integration. Now from the numerator m and denominator m cancels out. So ultimately I am left with 2 by pi b square minus a square, 2 by pi, not 2, it should be 4 by pi. It should be 4 by pi b square minus a square into r square integration d. Okay, and limit for r should be equals to from a to b, because inner radius is a, outer radius is b, so a to b is the limit. So it means r cube by 3. So it means 4 by 3 pi into b square minus a square and r cube. So r cube means b cube minus a cube. So in the numerator it will give b cube minus a cube. Okay, so that is the answer. So you can further simplify it by factorizing b cube minus a cube and b square minus a square. One term will cancel out. So ultimately you can simplify it, but that is the answer. Okay, so this is the idea how you are taking the element. Okay, so moving on to the next equation. Now I am considering the concept of rotation. So there is a rod which is rotating about this vertical axis with omega, let us say. So you are asked to calculate the moment of inertia of this uniform rod of mass m and length l about an axis passing through one end, making an angle theta equals to 45 degree with length. Okay, so that theta may be any angle. So for this, I have to take again about the rod. So by moving a distance of x, I am taking an element of with dx. Okay, now for this element, I want to calculate what is the mass of this element. So let us say mass of the element is dm. Okay, so what is the mass? So for this I define the lambda. Now what is lambda? Lambda is total mass is m, and length of the element, length of the rod is, let us say, l. So lambda is m by l. Corresponding to that, what is the dm number? So dm should be lambda times dx. Dm should be lambda times dx. Now put the value of lambda, that should be m by l into dx. Now this dm mass is rotating about this vertical axis at a distance of this much. Let us say this is r distance. So for this dm mass, can I write di about this vertical axis should be equal to r square into dm. Okay, now what is r? Small r number is x sine theta. So that means x sine theta whole square into dm. Now dm is m by l into dx. Okay, so it gives the value of di. So what is the total I about this vertical axis? That should be equal to integration of d. Once I am doing the integration, only variable is x. So take all the variable outside. It becomes sine square theta multiplied by m by l, come out of the integration. And ultimately I am getting the answer as integration of x square dx. Okay. So x square dx means putting the limit. Again I am putting the limit from 0 to L. So it becomes x cubed by 3. So answer is m L square by 3. So 1 L cancels out into sine square theta. Okay. Now since the theta is given as 45 degree, so if I put sine square theta, that should be half. So ultimately our answer should be m L square by 6. So that is the I value about this vertical axis. Okay. Or you can write it in this format also, where the variable is in terms of theta. Okay. So this is the another type of application where I am applying the same concept to calculate the moment of inertia. Okay. Now, apart from moment of inertia, I can also apply the same concept to calculate the torque also. So what is that? So there is a uniform disk of radius capital R is pinned at an angular velocity omega and then carefully placed on a horizontal surface such that it axis vertical. Okay. So how long will the disk be rotating on the surface if the friction coefficient is equal to 3? So because of friction, it will produce a guiding torque and ultimately the disk will stop. The pressure exerted by the disk on the surface can be regarded as uniform. Okay. Now what is the friction? So if I take an element on this disk, so by moving a distance of r from the center and taking a radius of dr, so can I say the friction acting on this particular surface is equals to mu into dm into g. Mu into dmg. Okay. What is dm? Dm is this torque. Dm is the elemental mass of this particular portion. Now what is this elemental mass? Dm can be written as sigma into dA. Okay, sigma into dA. Now what is sigma? Sigma is basically our total mass divided by area. Okay, sigma is total mass of the disk is, let us say, m divided by pi capital R square. So I have a sigma number. So I will put the sigma variation in the second part. Let us say I take the sigma number. So sigma into dA. Now regarding this ring element, what is the dA? That is m by pi R square is the sigma number into 2 pi small r into dr. That is the dm number. So correspondingly, the friction equals to how much? Friction is equals to mu. Mu is given as the k number, k into g into dm. So dm means m by pi r square into 2 pi r dr. There is a dm number. Okay. So this friction will produce a torque. This friction will produce a torque. What is the? So this is the elemental friction. So correspondingly, what is the elemental torque? So d tau about the center should be equals to f into small r. So df into small r is the elemental torque. So once I am multiplying it, so I am getting mkg divided by pi r square into 2 pi small r into again r. So 2 pi r square into dr. So cancel this pi number. So m k g 2 divided by capital R square into R square dr. That is the total elemental torque. Okay. So corresponding to that, what you can say, you can calculate the total torque acting on this. So total torque should be equal to tau should be equal to integration of d tau. So once I do the integration, so it gives 2m a g divided by R square into R cube by 3. Capital R cube by 3. Why I am putting the limit from 0 to capital R? So ultimately what I am getting 2 by 3 mkg into R. So that is the net torque, total torque acting about the center. Now because of this torque, what is happening? The angular retardation takes place. What is the retardation? So alpha can be written as tau divided by I. So I is the momentum inertia of the disk. That is equals to mr square by 2. So tau is equals to how much? 2 by 3 mgr into k. That is the torque divided by disk is mr square by 2. Okay. So corresponding to that, what I am getting that 4 kg divided by 3r. 4 kg by 3r. That is the value of alpha. That is the retardation. Okay. So initially the disk starts with an angular velocity of omega. So finally it stops and you are asked to calculate the time. So omega final, that should be equal to omega initial minus alpha into t. Okay. So omega final is 0. Omega initial is given as omega. So that should be equal to alpha into t. So from that I can calculate the value of t. That should be equal to omega by alpha. So final answer should be equal to how much? So 3 capital R omega divided by 4 kg. That is your answer. This is the time after which the disk will stop. Okay. So here you have to apply the concept of torque. You have to apply the concept of friction. Okay. And then you use the kinematics formula to calculate how much time it will be taken by the disk to stop. Okay. Now moving on to the next application. Now the topic is from gravitation. So here there is a wire, semicircular wire AB, whose mass is m and length L is given. And that wire is bent in the form of a semicircle. Now you are asked to calculate the field at point O. Field at point O. So first of all, so total mass of the ring is given as m, length is given as L. So I can write L equals to pi times capital R. So R is the radius of the semicircle. Okay. So from that I am getting the expression for the R. So what is R? R is equals to L by pi. R equals to L by pi, first one. And what is lambda? For this geometry, lambda should be equals to mass per unit length, that is m by L. Okay. Now for this element, let us say this is the element for this ring. So let us say moving from O at an angle of theta, I take an element of the theta. Okay, so this is the element. So what is this dm number? So dm should be equals to lambda times r d theta. Lambda into r d theta. Okay, so that is m by l into r d theta. That is the elemental mass. Now for this elemental mass dm, the field produced at this point should be in this direction. Now, so similarly, diametrically opposite, there will be another dm mass. So for this dm, the field will be in this direction. Now, if you take this component, so the cos component, that is the horizontal component, cancels out. So only we are left with the vertical component. What is the vertical component? That is dg sine theta. So net field at point O, that should be equals to integration of dg sine. So integration of dg sine theta is the net gravitational field that I want to calculate. G net. So what is the dg number? So dg is the elemental gravitational field produced by the dm. That should be g dm divided by r square into sine theta. Integration of this. Now put the value of dm. So dm is m by l into r d theta. M by l into r d theta. So capital G m by l into r d theta is the dm number divided by r square into sine theta. Integration. Now 1 r will cancel out. So in the numerator I am getting 1 r. So what is r? R equals to l by pi. So ultimately becomes g m pi by l square into sine theta d theta. That is the integration. So what is the limit? Limit is from 0 to pi. 0 to pi. Okay, 0 to pi is the limit. So ultimately what is the answer? So it should be g m pi by l square into minus cos theta. Integration of 0 to pi. So cos pi is minus 1. Again cos 0 is minus 1. So ultimately gives 2. So 2 g m pi by l square. Okay, that will be your answer. 2 g m pi by l square, and that should be along the vertical y direction. So answer will be 2 pi g m by l square along positive y direction. Okay, so that is your answer. So now moving on to the next type of problem where this is applied for the solid and fluid. Okay, first we discuss about the solid. So there is a bar of mass m and length l is hanging from the point S. The Young's modulus is y, area of cross section is constant, that is a given, find the total elongation. Okay, so for this again, let us say I move a distance of y from the bottom and I take an element like this dy thickness. Okay, I take an element of dy thickness. Now I want to check what is the elongation of this dy. Okay, so let us say dE is the elongation, elemental elongation of this dy length. Okay, now what is that dy? dE should be equals to our f l by ay. This is the formula of dE, small elongation. Now what is the f? F is the net force acting on this. So what is the force acting on this? So force acting on this is the weight of this bottommost part. Okay, so if I say weight of this bottommost part is how much? If I say the total length is L, so for this part, so what is the weight of this part? That should be equals to m by L is the mass per unit length multiplied by y into g. Okay, so that is the weight. So that is nothing but the force acting on this. So that is the force part. So m by L into y into g is the weight. Now what is L? L is the length of the element. Now length of the element is taken to be as a dy. You have an area of cross section is a, and Young's modulus is given as y. Okay, so once I simplify this, so it gives m g by a l y into y dy. Okay, so total elongation should be equals to E, that should be equals to m g by a l y taken out, integration of y dy, limit from 0 to L. Okay, so ultimately become L square by 2. So ultimately become mgl by 2ay. mgl by 2a into y. Okay, that is the total elongation. So this is the elongation due to the self weight. Okay, so rod having some kind of weight. Because of that, what is the small elongation that we first calculate? So this is what? This is the small elongation of the element. So once I calculate that, so then you have to integrate it to get the total elemental weight in elemental elongation. So next is, let us say, now the same thing is there. Only thing is that now the radius is changed. Let us say the body of mass 3.14 kg is suspended from one end of the wire of length 10 meter. Okay. So from here, the body is being suspended. Okay. The radius of cross section of the wire is changing uniformly from this number at the top to that number at the bottom. So that is, let us say R1, that should be, let us say, I say this radius is A given and this radius is B given. Okay, it is changing uniformly. So that is variation is linear. So Young's modulus is given as this number, the change in length of the wire. So again, I have to take about this situation. So this is the length. So let us say this is the body. So body is suspended from this, whose mass is m is given. Whose mass is given as m. So for this, if I move a distance of, let us say at this distance, let us say I move a distance of x from here and I take an element of this. The element of this. So whose thickness is dx? Let us give thickness is dx. And whose radius is smaller? Let us say this radius is smaller. Okay. So what I can write that, let us say the element having a mass of how much? Mg. Element is having a mass of mg. So what you can write that small elongation of this element, let us say dE is the small elongation. That should be equal to again L by Ay. Okay. Now what is F? F is the force acting on this element. Force acting on this element. So what is that force? That force is nothing but our mg force. Okay. So that is the force acting on this mg force. Mg is there. What is the length of this element? Length of the element is dx. What is the area? That's equal to pi r square, and Young's modulus is given as y. Okay. So you have to calculate the r number. You have to calculate the r number first. So how to calculate the r number? So for that you have to take about the similar triangle. So once I do the similar triangle analysis, so I can write that r should be equals to a plus b minus a by L into x. That is R number. So once we put this R number, so then R becomes function of x. R becomes function of x. Or we can take about the dx also. Now what is dx? So if I take integration as a function of R, so if I differentiate dr should be equal to b minus a by L into dx. Okay. B minus a by L into dx. So now what I can write, that number is equals to, if I say integration of d, I want to get, that is the total elongation delta. So that should be equals to how much? Integration of mg into dx. Instead of dx, write b minus a by L. Instead of dx, you write L into dr by b minus a. L into dr. Here I am writing A into dr divided by b minus a is the value of dx divided by pi r square. Divided by pi r square into 1. Okay, integration of this. So now I have changed the variable in terms of the r now. So ultimately what I am getting, that mg L by b minus a y, it comes out of the integration. So mg L divided by b minus a into y comes out of this integration, and again pi is also there. Pi is also there. So ultimately integration of dr by r square. Integration of dr by r square. Limit is from r variation. R is starting from a to b. So integration limit is from a to b. A to b. So dr by r square is minus 1 by r. So ultimately I am getting b minus, if I put the limit. So once I put the limit, so this number becomes b minus a by ab. Okay. And this multiplied by mg L divided by pi into b minus a into y. So b minus a cancels out. So ultimately what I am getting, that mg L divided by pi ab into y. That is the answer. Okay. So all the information is given. So m is 3.14 kg, that number is given. So m and pi will cancel out. So I am left with GL by AB into Y. Okay. So answer for the delta E should be equals to GL by AB into Y. What is G? G, if I take the value as G equals to 10, and G is not 10, I take it as 9.8 into length of the end is given as how much? Length is equals to 10 meter. This 10. Okay. Now AB, A is given as 5 and is 9.8. So 5 into 9, so 5 into 9.8 into 10 to the power minus 4 means minus 8 into Y. Young's model is 2 into 10 to the power 11. 2 into 10 to the power 11. So that is our answer. So 9.8, 9.8 cancels out. So 5 2s are 10 means 10 to the power 12. 11 and 12 minus 8 means plus 4. So once it goes up in the numerator, so minus 4, so minus 3. So 10 to the power minus 3 meter is your answer. Okay. So this is the 11. Option C is the correct one. Okay. So in this situation, what is I am doing? I have changed the integration. Instead of doing the integration with respect to x, I have changed the integration from x to r. So that will make the things easier. Okay. So now moving on to the next situation. Let us say there is a dam wall which is inclined at an angle theta to the horizontal. On one side of the wall, there is a water or liquid of height h is there. Now you are asked to calculate the force acting due to the liquid per unit weight. Okay. Now on this one, the pressure of the liquid is coming in this direction. Okay. Pressure. Now because of the pressure, the wall will feel a force. Wall will feel a force. Let us take this as this type. So let us say this is the wall. So at a distance of x, moving from this direction, I take an element of this dx. Okay. So I want to take what is the force on this element. Let us say this is the dx element. Let us say this is the dx element. So here the force acting is df. Force acting on this element is df. So what is df? Df should be equals to P into area of this element. Now what is the area? So width of the plate is given. Nothing is given. So if I say width of the plate, let us say this is the plate. So this is the cross section. So I can take this is the width. This is the width. So let us say this is 1 meter. So 1 meter is the width. So what is the area? So area of this element is dx. Okay. Now I want to calculate the df. So df should be equals to pressure on that particular point into dA. No, for pressure you have to calculate the vertical length. You have to calculate the vertical length. So I am moving a distance of x from the free surface. So what is, let us say this is the distance x moved from the free surface. So what is the vertical length then? So vertical length is this much distance. This is the distance. Okay. So if I say this is x, so the angle is also theta. So vertical length is x sine theta. So at that particular point, P equals to how much? Rho g into x sine theta. There the P into dA is dx. Integration of that will be the total force F. Okay. So that means I am getting rho g sine theta integration of x dx. And limit of x is from 0 to L. Okay. Per unit width. And the length of this x is given. Instead of x, the value of h is given. Okay. So what is this x number then? X number should be h by sine theta. So if I say this is the total length L. Okay. So the vertical height is h. Vertical is h. So there means theta. So L sine theta is equals to h. So L sine theta equals to h. What is the L number? So h by sine theta. So limit is from 0 to L. Now what is L? L is equals to h by sine. Now h by sine theta. So that means x square by 2. X given x square by 2 means 0 to rho g sine theta into L square by 2. Now what is L square? L square is h square divided by sine square theta. So ultimately one sine theta cancels out. So I am getting rho g h square by 2 sine theta. Okay. Rho g h square by 2 sine theta, that will be your answer. Option A. Okay. So here you have to take an element and on that element you have to calculate the force. So in order to calculate the force, so water is there on the other surface. So you are moving this vertical distance. So at a depth of h below the liquid surface, the pressure is equal to rho g h. But here h is equal to g sine theta. Okay. Now moving on to the next situation, here I am applying the concept of thermal properties. So coefficient of linear expansion alpha of a rod is given as equals to alpha naught plus alpha 1x, where alpha naught and alpha 1 are constant. So you are asked to calculate the increasing length when it is heated up to 100 degrees Celsius. Okay. So let us say this is a rod. Let us say this is a rod. So if I move a distance of x from here and I take an element of dx, I want to check what is the elemental elongation of this element. Okay, small elongation of this element. Okay, so let us say there is a small temperature difference of delta T. Let us say for the temperature difference of delta T, what is the dl elemental elongation change? That should be equal to L alpha into delta T. Okay, what is this L number? L number is the elemental length. Okay, so this is the formula for the elongation, elemental elongation. That should be equal to dl should be equal to L alpha delta T. What is L? L is the length of the element, so that is dx. Now what is alpha? Alpha is variation given as alpha naught plus alpha 1 into x. Okay, and dt is delta T, that is given. Okay, so total elongation, that is delta L, that is elemental elongation integration of that number, that is equals to how much? That delta T comes out alpha naught plus alpha 1 x dx integration. So ultimately I am getting alpha naught into x plus alpha 1 into x square by 2 into delta T. Limit is from 0 to L. 0 to total length of the element is L, so 0 to L. So ultimately our answer will be delta T multiplied by alpha naught into L plus alpha 1 into L square by 2. Alpha naught into L square by 2. So once I put this value of alpha naught and alpha 1 along with the capital L and delta T. What is delta T? Delta T is 100 degrees Celsius given. So that number is delta T. Once I put all those variables into the finally formula, so in this final expression, so once I put all those numbers, so ultimately I am getting the answer as 3.76 millimeter. So that will answer 3.76 millimeter. Okay. So this is the one application. Now come to the wave motion application. So there is a loop of rope wheel at an angular velocity omega, so that it becomes taut, circle of radius r. A kink develops in the wheeling rope. Okay. So the speed of the kink of the rope is v equals to omega. Okay, so once you rotate this, so it will develop a kink. Now we want to calculate what is the speed of this kink in the rope. Okay, so for this situation, now this entire rope, loop or rope will be under tension. So once I rotate it, it will be under tension. So first you have to calculate what is the tension of that particular rope. Okay, so let us say this is a rope that is being wheeled. So for this situation, what you consider about the center, if I take an element like this, let us say this angle is d theta, this angle is also d theta. Okay. So for this situation, see if I say this end of the string is experiencing a T tension, so that is also experiencing tension T. Okay. So component of T along horizontal direction will be how much? D theta. So d cos d theta. That should be equal to d cos of d theta. Similarly, that component is also t cos d theta. So vertical component will be sine component, and that will be balanced by the force, that is the centrifugal force, dm. What is dm? Dm is the mass of this end of this rope. So dm into omega square into capital R. Okay. So ultimately, what you can write that 2t sine of d theta, that is a vertical component, that is balanced by dm into omega square into r. Now what is dm? dm is the total mass. dm is the elemental mass. So elemental mass is how much? Length. m is, let us say, mass. Length of the rope is how much? 2 pi capital R. Okay. Into r times 2 d theta. R times 2 d theta is the length. Multiplied by omega square into r. And that is equal to 2t sine of d theta. Now since d theta angle is very, very small, so I can approximate that sine of d theta is equals to d theta. So on the left hand side I am getting t into 2 d theta. That should be equals to r will cancel out, 2 will cancel out. So m by pi omega square into r into d theta. So ultimately d theta cancels out. So I am getting T equals to capital T tension equals to A omega square R divided by 2 pi. So this is the tension developed in the rotating loop. And now, because of the tension, now the loop has developed a kink. Okay, loop has developed a kink. So that under the tension, I want to calculate what is the speed which is the kink of the rope is moving. Okay, so there is a wave generated and that is moving with a velocity v, and that is equal to under t by mu. If that string is under tension, so the velocity with which the wave is moving, that is the speed of the wave, that is equal to under t by mu. So I have already got the value of T is equals to A omega square R by 2 pi. Now what is mu? Mu is the mass per unit length. So A means the mass. Unit length is how much? 2 pi R, 2 pi capital R. So ultimately A 2 pi cancels out. So ultimately I am getting omega square into R square. That is omega into R. Okay, so this is the velocity which is the wave that has been generated is moving. Okay, so this is the answer then. Now moving on to the next situation. Here there is a parallel plate capacitor of area A and the gap between them is small. Now the gap is filled with a dielectric constant which varies along the y edge. Here lambda into pi y by 2d. That is the variation that is given. Where lambda is the dimensional constant, the capacitance of this capacitor. So for this, if the capacity is varying, the dielectric constant is varying on the y direction. So for this thing, you have to move a distance of y and then take an element of dy thickness. So this is the small capacitor that I am talking about, whose thickness is dy. Okay, so like this way, all the plates can be plotted. So all this dy thickness capacitor are arranged in such a way so that the net capacitance becomes a C. Okay, so let us say this capacitance is DC. So all these DCs are arranged in series combination. Okay, all these DCs are arranged in series combination. So what is the C equivalent? So I can see that 1 by C equivalent should be equals to integration of 1 by DC. That is our number. So I want to calculate what is the DC number. So for DC, I should use the formula that is equals to epsilon naught A by B. There is the formula. What is epsilon? That is constant epsilon naught. What is area? That is the area of this plate. Okay. So if I say the area is capital A, so that is A, and D is what? D is the thickness. So that is dy. Now since the plate is filled with the capacitor of dielectric constant K, so multiply by K. So K is how much? So K is equals to, so it is equals to given as lambda sec of pi y by 2d. Okay, so that is the DC number. So you have to take about the 1 upon DC. Why? Because it is reciprocal. So 1 upon DC becomes how much? The entire thing goes in the numerator and denominator will be reversed. So I write directly 1 upon DC equals to how much? Lambda into A into epsilon naught in the denominator. Epsilon naught A into lambda is in the denominator. And sec becomes cos into dy. So cos of pi y by 2d into dy. That is the integration. Okay. So ultimately what I am getting that is the number. So cos theta. So cos theta, if I do the integration, so here the limit is from 0 to our d. D is the gap. So 0 to d. Okay. So once I do this integration, so cos theta becomes sin theta, but here so 2d by pi will be multiplied. Yeah, divide by 2d by pi. So it should be equals to sin of pi y by 2d whole divided by pi by 2d multiplied by 1 upon epsilon naught a into lambda. Okay. Now here I have to put the limit of 0 to d. So for d it becomes pi by 2. For 0 becomes 0. Okay, so pi by 2 means 1. So 1. So ultimately what I am getting, so it gives 2d by epsilon naught a lambda into pi. Okay. So ultimately that is just 1 upon C equivalent. So C equivalent should be how much? So C equivalent should be equals to epsilon naught A lambda pi divided by 2. That will be your answer. Okay, so that is first one. Okay, so depending on the variation, so in this situation, the capacitance may also be a variable of x. So once there is a variation is in terms of x, so you have to take the horizontal element, and in that situation, all the elements will be in parallel combination. Okay. Now moving on to the next situation where I am going to apply the same concept for the magnetism. So there are two long thin parallel conductors of the shape I1 and I2 are current is influence. The separation between the conductor is A and the width of the right hand conductor is equals to B. So there is a width of conductor of the right hand part is B, and you are asked to calculate the magnetic interaction force between them reduced to individual layer. Individual layer. Okay. So how to calculate that? So for that, so if there are if there are two wire carrying current in the same direction, so I know how to calculate the magnetic field and corresponding to that, what is the force? Okay. So if I take an element like this way, let us say I take an element by moving a distance of x from here, and I took an element like this of thickness dx. Okay. Now for this dx, let us say the I amount of current is inflowing. I current is inflowing. Now these two wires are carrying the same current in the same direction. So force per unit length. Force per unit length should be written as, what is the formula for force per unit length? So that should be equal to mu naught I1 I2 divided by 2 pi d. So there is a force of interaction between the two wire carrying parallel current. So here the question is given that L is, we are taking the L as 1 meter. So for this equation, I want to calculate what is the I first. So here the df number in this situation, df should be equals to how much? Df should be equals to mu naught I1 into I2 means I divided by 2 pi, and what is the d? D is our x number. Now what is I? So I is this current. So what is this I? So total I is flowing through this element is I2. So I2 per unit width is I2 divided by B into dx. That is basically I number. So this can be written as a mu naught I1 divided by 2 pi x, and for I am writing I2 by B into dx. So this is the elemental force. This is the elemental force. So once I integrate this, that will be the total force. So that means mu naught I1 I2 divided by 2 pi B out integration of dx by x. That will be the total force F total. Okay. Now regarding the elemental length x dx, now you have to put the limit of x. So x is starting from point A to A plus B. So lower limit is A, upper limit is A plus B. Okay, so ultimately I am getting mu naught I1 I2 divided by 2 pi B into ln x. Ln x means ln A plus B by A. Ln A plus B divided by A. That will be your answer. Okay. So this is the force acting on this wire. Okay. Now, the same question. There is a copper rod of length this much is moving with a uniform velocity 10 meter per second parallel to a long straight current carrying wire. So let us say this is the infinitely carrying current wire of carrying let us say I is the current. Okay. Now there is another conductor. Let us say this is the conductor AB. Now this AB wire is moving in this direction with the speed of V naught. You are asked to calculate the potential difference across this AB. Okay. So length is given. All these things are given. Okay. So let us say by moving a distance of x from this end, I take an element of dx. Okay, I take an element of dx. So this is our dx length. Here dx length. So for this element dx, so this dx is moving with v naught speed upward. So if I closely look at the dx element, what I can say that dx element is this one. It is moving in the upward direction, v naught. And for this current carrying y, magnetic field will be at this position is the cross magnetic field. So under the cross magnetic field, if the magnetic conductor is moving in the upward direction, so V cross B, that means this side is the positive potential and this side is the negative potential. The small induced potential, induced EMF that has been generated, B epsilon, and written as V naught into VB. So V naught is the velocity. V is the magnetic field over here. So what is magnetic field due to infinitely carrying current? Where? It is mu naught I by 2 pi x. Okay. And what is the length? Length is dx. Okay. So I am applying the formula epsilon induced should be equals to VVL. What is V? V is the velocity, which is the conductance moving, that is V naught. V is the magnetic field created at that particular point, and L is the length of the conductor. So this is a small induced EMF. So total induced EMF should be equals to integration of this. So V naught mu naught I by 2 pi out of this integration. So only thing the integration of dx by x. Okay. Now limit of x. So this value is given as, let us say, I am saying this value A, and length of the rod is L. So starting from A to A plus L. So ultimately I am getting V mu naught into V naught into I divided by 2 pi into ln A plus L by A. Okay. So in the numerical, all the values are given. Okay. So length of the wire is given as 0.19 meters. So L is given as 0.1. L is 0.19. Okay. Velocity V naught is given as 10 meter per second. Now I is given as 5 ampere. A inside distance of 0.01 meter and 0.2 meter from it. Okay. So 0.01 meter and 0.2 meter, that means 0.01 is the A number. So A number is equal to 0.01 meter. Okay. That will be A into. So all the answers you are getting. So ultimately what you can say, you can put this number. Then ultimately once we calculate this number, so this number comes to be a 3 into 10 to the power minus 5 volt. That will be your answer. Okay, 3 into 10 to the power minus 5. Okay. So these are different types of applications. Hope you understand this. So very carefully apply the concept and try to solve this numeric. So these are typical applications where I am going to apply the concept of integration. Hope you understand this. Stay tuned for the next video again. If you like it, please subscribe my channel. Okay, thank you and bye.